Learning objectives. In this chapter, the user will learn the following in detail. Data pre-processing, including data cleaning, data integration, data transformation, discretization and concept hierarchy generation, definition and specification of a generic data mining task, description of data mining query language with few example queries. Concept hierarchy generation. Concept hierarchy generation for nominal data. Nominal attributes have a finite, but possibly large number of distinct values with no ordering among the values. Manual definition of concept hierarchies can be a tedious and time-consuming task for a user or domain expert. Fortunately, many hierarchies are implicit within the database schema and can be automatically defined at the schema definition level. The concept hierarchies can be used to transform the data into multiple levels of granularity. For example, data mining patterns regarding sales may be found relating to specific regions or countries, in addition to individual branch locations. 4 methods for the generation of concept hierarchies for nominal data as follows. Specification of a partial ordering of attributes explicitly at the schema level by users or experts. Concept hierarchies for nominal attributes or dimensions typically involve a group of attributes. A user or expert can easily define a concept hierarchy by specifying a partial or total ordering of the attributes at the schema level. For example, suppose that a relational database contains the following group of attributes: street, city, province or state, and country. Similarly, a data warehouse location dimension may contain the same attributes. A hierarchy can be defined by specifying the total ordering among these attributes at the schema level, such as street belongs to city belongs to province or state belongs to country. Specification of a portion of a hierarchy by explicit data grouping. This is essentially the manual definition of a portion of a concept hierarchy. In a large database, it is unrealistic to define an entire concept hierarchy by explicit value enumeration. On the contrary, we can easily specify explicit groupings for a small portion of intermediate level data. For example, after specifying that province and country form a hierarchy at the schema level, a user could define some intermediate levels manually, such as Alberta, Saskatchewan, Manitoba, proper subset of Prairies, Canada, and British Columbia, Prairies, Canada, as proper subset of Western Canada. Specification of a set of attributes but not of their partial ordering. A user may specify a set of attributes forming a concept hierarchy but omit to explicitly state their partial ordering. The system can then try to automatically generate the attribute ordering so as to construct a meaningful concept hierarchy. A concept hierarchy can be automatically generated based on the number of distinct values per attribute in the given attribute set. The attribute with the most distinct value is placed at the lowest hierarchy level. The lower the number of distinct values an attribute has, the higher it is in the generated concept hierarchy. This heuristic rule works well in many cases. Some local level swapping or adjustments may be applied by users or experts when necessary after examination of the generated hierarchy. Specification of only a partial set of attributes. Sometimes a user can be careless when defining a hierarchy or have only a vague idea about what should be included in a hierarchy. Consequently, the user may have included only a small subset of the relevant attributes in the hierarchy specification. Figure shows the automatic generation of a schema concept hierarchy based on the number of distinct attribute values. Data cleaning. Real-world data tend to be incomplete, noisy, and inconsistent. Data cleaning or data cleansing routines attempt to fill in missing values, smooth out noise while identifying outliers, and correct inconsistencies in the data. Missing values. Imagine that you need to analyze all electronic sales and customer data. You note that many tuples have no recorded value for several attributes such as customer income. How can you go about filling in the missing values for this attribute? Let's look at the following methods. Ignore the tuple. This is usually done when the class label is missing, assuming the mining task involves classification. This method is not very effective unless the tuple contains several attributes with missing values. It is especially poor when the percentage of missing values per attribute varies considerably. By ignoring the tuple, we do not make use of the remaining attributes' values in the tuple. Such data could have been useful to the task at hand. Fill in the missing value manually. In general, this approach is time-consuming and may not be feasible given a large data set with many missing values. Use a global constant to fill in the missing value. Replace all missing attribute values by the same constant such as a label like unknown or -infinity. If missing values are replaced by, say, unknown, then the mining program may mistakenly think that they form an interesting concept since they all have a value in common, that of unknown. Hence, although this method is simple, it is not foolproof. Use a measure of central tendency for the attribute to fill in the missing values. A measure of central tendency indicates the middle value of a data distribution. For normal symmetric data distributions, the mean can be used, while skewed data distribution should employ the median. For example, suppose that the data distribution regarding the income of all electronics users is symmetric and that the mean income is $56,000. Use this value to replace the missing value for income. Use the attribute mean or median for all samples belonging to the same class as the given tuple. For example, if classifying customers according to credit risk, we may replace the missing value with the mean income value for customers in the same credit risk category as that of the given tuple. If the data distribution for a given class is skewed, the median value is a better choice. Use the most probable value to fill in the missing value. This may be determined with regression, inference-based tools using a Bayesian formalism, or decision tree induction. For example, using the other customer attributes in your dataset, you may construct a decision tree to predict the missing values for income. Methods 3 through 6 bias the data. The filled-in value may not be correct. Method 6, however, is a popular strategy. In comparison to the other methods, it uses the most information from the present data to predict missing values. By considering the other attributes' values in its estimation of the missing value for income, there is a greater chance that the relationships between income and the other attributes are preserved. Noisy data. What is noise? Noise is a random error or variance in a measured variable. Given a numeric attribute such as, say, price, how can we smooth out the data to remove the noise? Let's look at the following data smoothing techniques. Binning. Binning methods smooth a sorted data value by consulting its neighborhood, that is, the values around it. The sorted values are distributed into a number of buckets or bins. Because binning methods consult the neighborhood of values, they perform local smoothing. In this example, the data for price are first sorted and then partitioned into equal frequency bins of size 3. That is, each bin contains 3 values. In smoothing by bin means, each value in a bin is replaced by the mean value of the bin. For example, the mean of the values 4, 8 and 15 in bin 1 is 9. Therefore, each original value in this bin is replaced by the value 9. Similarly, smoothing by bin medians can be employed, in which each bin value is replaced by the bin median. In smoothing by bin boundaries, the minimum and maximum values in a given bin are identified as the bin boundaries. Each bin value is then replaced by the closest boundary value. In general, the larger the width, the greater the effect of the smoothing. Alternatively, bins may be equal width, where the interval range of values in each bin is constant. Regression. Data smoothing can also be done by regression, a technique that conforms data values to a function. Linear regression involves finding the best line to fit 2 attributes or variables so that one attribute can be used to predict the other. Multiple linear regression is an extension of linear regression where more than 2 attributes are involved and the data are fit to a multi-dimensional surface. Outlier analysis. Outliers may be detected by clustering, for example, where similar values are organized into groups or clusters. Intuitively, values that fall outside of the set of clusters may be considered outliers. Figure shows a 2D customer data plot with respect to customer locations in a city showing 3 data clusters. Outliers may be detected as values that fall outside of the cluster sets. Data cleaning as a process. Missing values, noise, and inconsistencies contribute to inaccurate data. The first step in data cleaning as a process is discrepancy detection. Discrepancies can be caused by several factors, including poorly designed data entry forms that have many optional fields, human error in data entry, deliberate errors, such as respondents not wanting to divulge information about themselves, and data decay, outdated addresses. Discrepancies may also arise from inconsistent data representations and inconsistent use of codes. Other sources of discrepancies include errors in instrumentation devices that record data and system errors. Errors can also occur when the data are inadequately used for purposes other than originally intended. There may also be inconsistencies due to data integration, where a given attribute can have different names in different databases. Discrepancy detection. Look out for the inconsistent use of codes and any inconsistent data representations. For example, 2010-12-25 and 25-12-2010 for date. Field overloading is another error source that typically results when developers squeeze new attribute definitions into unused bit portions of already defined attributes. For example, an unused bit of an attribute that has a value range that uses only, say, 31 out of 32 bits. The data should also be examined regarding unique rules, consecutive rules, null rules. A unique rule says that each value of the given attribute must be different from all other values for that attribute. A consecutive rule says that there can be no missing values between the lowest and highest values for the attribute, and that all values must also be unique, as in check numbers. A null rule specifies the use of blanks, question marks, special characters, or other strings that may indicate the null condition. Example, where a value for a given attribute is not available, and how such values should be handled. The null rule should specify how to record the null condition, for example, such as to store 0 for numeric attributes, a blank for character attributes, or any other conventions that may be in use. For example, entries like don't know or question mark should be transformed to blank. There are a number of different commercial tools that can aid in the discrepancy detection step. Data scrubbing tools use simple domain knowledge, that is, knowledge of postal addresses and spell checking, to detect errors and make corrections in the data. These tools rely on parsing and fuzzy matching techniques when cleaning data from multiple sources. Data auditing tools find discrepancies by analyzing the data to discover rules and relationships and detecting data that violate such conditions. They are variants of data mining tools. For example, they may employ statistical analysis to find correlations or clustering to identify outliers. Correcting data inconsistency. Some data inconsistencies may be corrected manually using external references. Most errors, however, will require data transformations. That is, once we find discrepancies, we typically need to define and apply a series of transformations to correct them. Commercial tools can assist in the data transformation step. Data migration tools allow simple transformations to be specified, such as to replace the string gender by sex. ETL, extraction transformation loading, tools allow users to specify transforms through a graphical user interface GUI. These tools typically support only a restricted set of transforms, so that often we may also choose to write custom scripts for this step of the data cleaning process. The two-step process of discrepancy detection and data transformation iterates. This process, however, is error-prone and time-consuming. Transformations are often done as a batch process while the user waits without feedback. Only after the transformation is complete can the user go back and check that no new anomalies have been mistakenly created. Typically, numerous iterations are required before the user is satisfied. Another approach to increased interactivity in data cleaning is the development of declarative languages for the specification of data transformation operators. Data discretization. Let A be a numeric attribute with n observed values, v1 going up to vn. Min-max normalization performs a linear transformation on the original data. Suppose that min A and max A are the minimum and maximum values of attribute A. Min-max normalization maps a value vi of A to v dash I in the range new min A to new max A by computing vi dash equals vi minus min A divided by max A minus min A into new max A minus new min A plus new min A. Min-max normalization preserves the relationships among the original data values. It will encounter an outer bounds error if a future input case for normalization falls outside the original data range for A. Discretization by binning. Binning is a top-down splitting technique based on a specified number of bins. These methods are also used as discretization methods for data reduction and concept hierarchy generation. For example, attribute values can be discretized by applying equal width or equal frequency binning, and then replacing each bin value by the bin mean or median, as in smoothing by bin means or smoothing by bin medians, respectively. These techniques can be applied recursively to the resulting partitions to generate concept hierarchies. Binning does not use class information and is therefore an unsupervised discretization technique. It is sensitive to the user-specified number of bins as well as the presence of outliers. Discretization by histogram analysis. Like binning, histogram analysis is an unsupervised discretization technique because it does not use class information. A histogram partitions the value of an attribute A into disjoint ranges called buckets or bins. Various partitioning rules can be used to define histograms. In an equal width histogram, for example, the values are partitioned into equal size partitions or ranges. With an equal frequency histogram, the values are partitioned so that ideally each partition contains the same number of data tuples. The histogram analysis algorithm can be applied recursively to each partition in order to automatically generate a multi-level concept hierarchy, with the procedure terminating once a pre-specified number of concept levels has been reached. A minimum interval size can also be used per level to control the recursive procedure. This specifies the minimum width of a partition or the minimum number of values for each partition at each level. Histograms can also be partitioned based on cluster analysis of the data distribution. Discretization by cluster, decision tree, and correlation analyses. Clustering, decision tree analysis, and correlation analysis can be used for data discretization. Cluster analysis is a popular data discretization method. A clustering algorithm can be applied to discretize a numeric attribute A by partitioning the values of A into clusters or groups. Clustering takes the distribution of A into consideration as well as the closeness of data points and therefore is able to produce high-quality discretization results. Clustering can be used to generate a concept hierarchy for A by following either a top-down splitting strategy or a bottom-up merging strategy, where each cluster forms a node of the concept hierarchy. In the former, each initial cluster or partition may be further decomposed into several subclusters, forming a lower level of hierarchy. In the latter, clusters are formed by repeatedly grouping neighboring clusters in order to form higher-level concepts. Techniques to generate decision trees for classification can be applied to discretization. Such techniques employ a top-down splitting approach. Unlike the other methods mentioned so far, decision tree approaches to discretization are supervised, that is, they make use of class label information. Class distribution information is used in the calculation and determination of split points, data values for partitioning an attribute range. Intuitively, the main idea is to select split points so that a given resulting partition contains as many tuples of the same class as possible. Entropy is the most commonly used measure for this purpose. To discretize a numeric attribute A, the method selects the value of A that has the minimum entropy as a split point and recursively partitions the resulting intervals to arrive at a hierarchical discretization. Such discretization forms a concept hierarchy for A. Because decision tree-based discretization uses class information, it is more likely that the interval boundaries, split points, are defined to occur in places that may help improve classification accuracy. Measures of correlation can be used for discretization. Chi-merge is a chi-squared based discretization method. The discretization methods that we have studied up to this point have all employed a top-down splitting strategy. This contrasts with chi-merge, which employs a bottom-up approach by finding the best neighboring intervals and then merging them to form larger intervals recursively. As with decision tree analysis, chi-merge is supervised in that it uses class information. The basic notion is that for accurate discretization, the relative class frequency should be fairly consistent with an interval. Therefore, if two adjacent intervals have a very similar distribution of classes, then the intervals can be merged. Otherwise, they should remain separate. Chi-merge proceeds as follows. Initially, each distinct value of a numeric attribute A is considered to be one interval. Chi-square tests are performed for every pair of adjacent intervals. Adjacent intervals with the least chi-square values are merged together, because low chi-squared values for a pair indicate similar class distributions. This merging process proceeds recursively until a predefined stopping criterion is met. Data integration. Data mining often requires data integration, the merging of data from multiple data stores. Careful integration can help reduce and avoid redundancies and inconsistencies in the resulting data set. This can help improve the accuracy and speed of the subsequent data mining process. The semantic heterogeneity and structure of data pose great challenges in data integration. Entity identification problem. Data analysis task involves data integration, which combines data from multiple sources into a coherent data store, as in data warehousing. These sources may include multiple databases, data cubes, or flat files. There are a number of issues to consider during data integration. Schema integration and object matching can be tricky. How can equivalent real-world entities from multiple data sources be matched up? This is referred to as the entity identification problem. Metadata can be used to help avoid errors in schema integration. The metadata may also be used to help transform the data. When matching attributes from one database to another during integration, special attention must be paid to the structure of the data. This is to ensure that any attribute functional dependencies and referential constraints in the source system match those in the target system. Redundancy and correlation analysis. Redundancy is another important issue in data integration. An attribute may be redundant if it can be derived from another attribute or set of attributes. Inconsistencies in attribute or dimension naming can also cause redundancies in the resulting dataset. Some redundancies can be detected by correlation analysis. Given two attributes, such analysis can measure how strongly one attribute implies the other based on the available data. For nominal data, we use the chi-square test. For numeric attributes, we can use the correlation coefficient and covariance, both of which access how one attribute's values vary from those of another. Chi-square correlation test for nominal data. For nominal data, a correlation relationship between the two attributes, A and B, can be discovered by a chi-square test. Suppose A has C distinct values, namely A1, A2 going on up to AC. B has R distinct values, namely B1, B2 going on up to BR. Let AI, Bj denote the joint event that attribute A takes on a value Aj, AI, and attribute B takes on value Bj, that is, where capital A equals small ai, capital B equals small bj. The chi-square value, also known as the Pearson chi-square statistic, is computed as chi-square equals sigma I equals 1 to C, sigma j equals 1 to R, Oj minus Eij whole squared divided by Eij, where Oj is the observed frequency, actual count of the joint event A, I, B, J, and Eij is the expected frequency of Ai Bj, which can be computed as Eij equals count A minus small ai into count B minus small bj divided by n, where n is the number of data tuples. Count A equals ai is the number of tuples having value ai for A, and count B equals bj is the number of tuples having value bj for B. The chi-square statistic tests the hypothesis that A and B are independent, that is, there is no correlation between them. The test is based on a significant level with r-1 into c-1 degrees of freedom. Correlation coefficient for numeric data. For numeric attributes, we can evaluate the correlation between two attributes A and B by computing the correlation coefficient, also known as Pearson's product moment coefficient, named after its inventor Carl Pearson. This is RAB equals sigma I equals 1 to n brackets AI minus A bar into BI minus B bar. R of A and B equals summation I1 to n AI minus A bar BI minus B bar divided by n sigma A sigma B equals summation of I equals 1 to n AI into BI minus n A bar B bar divided by n sigma A sigma B, where n is the number of tuples, AI and BI are the respective values of A and B in tuple I, A bar and B bar are the respective mean values of A and B. Sigma A and sigma B are the respective standard deviations of A and B, and summation AI-BI is the sum of the AB cross product. Note that RAB lies between -1 and +1. If RAB is greater than 0, then A and B are positively correlated, meaning that the values of A increase as the values of B increase. The higher the value, the stronger the correlation. Hence, a higher value may indicate that A or B may be removed as a redundancy. If the resulting value is equal to 0, then A and B are independent and there is no correlation between them. If the resulting value is less than 0, then A and B are negatively correlated, where the values of one attribute increase as the values of the other attribute decrease. Correlation does not imply causality. That is, if A and B are correlated, this does not necessarily imply that A causes B or that B causes A. Covariance of numeric data. In probability theory and statistics, correlation and covariance are two similar measures for assessing how much two attributes change together. Consider two numeric attributes A and B and a set of n observations A1, B1 going up to AN, Bn. The mean value of A and B respectively are also known as the expected value on A and B, that is, expected A equals A bar equals summation I1 to n AI divided by n, and expected value of B equals, that is, B bar equals summation I1 to n Bi divided by n. The covariance between A and B is defined as covariance of A and B equals E into A minus A bar into B minus B bar equals summation of I1 to n AI minus A bar into Bi minus B bar divided by n. If we compare above equations, R, A and B equals covariance of A and B divided by sigma A, sigma B. Where sigma A and sigma B are the standard deviations of A and B respectively, it can also be shown that covariance of A and B equals expected value of A into B minus A bar B bar. This equation may simplify calculations. For two attributes A and B that tend to change together, if A is larger than 8 bar, the expected value of A, then B is likely to be larger than B bar, the expected value of B. Therefore, the covariance between A and B is positive. On the other hand, if one of the attributes tends to be above its expected value when the other attribute is below its expected value, then the covariance of A and B is negative. If A and B are independent, that is, they do not have correlation, then expected value of A dot B equals E of A into E of B. Therefore, the covariance is covariance A and B equals E of A dot B minus A bar B bar equals E of A into E of B minus A bar B bar equals 0. However, the converse is not true. Some pairs of random variables attributes may have covariance of 0 but are not independent. Only under some additional assumptions, that is, the data follow multivariate normal distributions, does a covariance of 0 imply independence. Tuple duplication. In addition to detecting redundancies between attributes, duplication should also be detected at the tuple level. The use of denormalized tables is another source of data redundancy. Inconsistencies often arise between various duplicates due to inaccurate data entry or update some but not all data occurrences. For example, if a purchase order database contains attributes for the purchaser's name and address instead of a key to this information in a purchase database, discrepancies can occur, such as the same purchaser's name appearing with two different addresses within the purchase order database. Data value conflict detection and resolution. Data integration also involves the detection and resolution of data value conflicts. For example, for the same real-world entity, attribute values from different sources may differ. This may be due to differences in representation, scaling, or encoding. For instance, a weight attribute may be stored in metric units in one system and British imperial units in another. Attributes may also differ on the abstraction level, where an attribute in one system is recorded at, say, a lower level of abstraction than the same attribute in another. For example, the total sales in one database may refer to one branch of all electronics, while an attribute of the same name in another database may refer to the total sales for all electronic stores in a given region. Data preprocessing. Data have quality if they satisfy the requirements of the intended use. There are many factors comprising data quality, including accuracy, completeness, consistency, timeliness, believability, and interpretability. Users of database system have reported errors, unusual values, and inconsistencies in the data recorded for some transactions. The data that is to be analyzed by data mining techniques are incomplete, lacking attribute values or certain attributes of interest, or containing only aggregate data, inaccurate or noisy, containing errors or values that deviate from the expected, and inconsistent, containing discrepancies in the department codes used to categorize items. Elements defining data quality, accuracy, completeness, and consistency. Inaccurate, incomplete, and inconsistent data are commonplace properties of large real-world databases and data warehouses. Inaccurate data. Reasons for inaccurate data. The data collection instruments used may be faulty. There may have been human or computer errors occurring at data entry. Users may purposely submit incorrect data values for mandatory fields when they do not wish to submit personal information. For example, by choosing the default value January 1 displayed for birthday. This is known as disguised missing data. Errors in data transmission can also occur. There may be technology limitations such as limited buffer size for coordinating synchronized data transfer and consumption. Incorrect data may also result from inconsistencies in naming conventions or data codes or inconsistent formats for input fields, for example, date. Duplicate tuples also require data cleaning. Incomplete data. Reasons for incomplete data. Attributes of interest may not always be available, such as customer information for sales transaction data. Other data may not be included simply because they were not considered important at the time of entry. Relevant data may not be recorded due to a misunderstanding or because of equipment malfunctions. Data that were inconsistent with other recorded data may have been deleted. Furthermore, the recording of the data history or modifications may have been overlooked. Missing data, particularly for tuples with missing value for some attributes, may need to be inferred. Data quality depends on the intended use of the data. Two different users may have very different assessments of the quality of a given database. Timeliness also affects data quality. Suppose that you are owing the distribution of monthly sales bonuses to the top sales representatives at All Electronics. Several sales representatives, however, fail to submit their sales records on time at the end of the month. There are also a number of corrections and adjustments that flow in after the month's end. For a period of time following each month, the data stored in the database are incomplete. However, once all of the data are received, it is correct. The fact that the month-end data are not updated in a timely fashion has a negative impact on the data quality. Two other factors affecting data quality are believability and interpretability. Believability reflects how much the data are trusted by users, while interpretability reflects how easily the data are understood. Suppose that a database at one point had several errors, all of which have since been corrected. The past errors, however, had caused many problems for sales department users, and so they no longer trust the data. The data also may use many accounting codes which the sales department does not know how to interpret. Even though the database is now accurate, complete, consistent and timely, sales department users may regard it as of low quality due to poor believability and interpretability. Major tasks in data preprocessing. The major steps involved in data preprocessing are data cleaning, data integration, data reduction, data transformation. Data cleaning. Data cleaning routines work to clean the data by filling in missing values, smoothing noisy data, identifying or removing outliers, and resolving inconsistencies. If users believe the data are dirty, they are unlikely to trust the results of any data mining that has been applied. Furthermore, dirty data can cause confusion for the mining procedure, resulting in unreliable output. Although most mining routines have some procedures for dealing with incomplete or noisy data, they are not always robust. Instead, they may concentrate on avoiding overfitting the data to the function being modeled. Therefore, a useful pre-processing step is to run your data through some data cleaning routines. Data integration. Suppose that you would like to include data from multiple sources in your analysis. This would involve integrating multiple databases, data cubes, or files, that is, data integration. Yet some attributes representing a given concept may have different names in different databases, causing inconsistencies and redundancies. For example, the attribute for customer identification may be referred to as customer ID in one data store and cust ID in another. Naming inconsistencies may also occur for attribute values. For example, the same first name could be registered as Bill in one database, William in another, and B in a third. Having a large amount of redundant data may slow down or confuse the knowledge discovery process. Clearly, in addition to data cleaning, steps must be taken to help avoid redundancies during data integration. Typically, data cleaning and data integration are performed as a pre-processing step when preparing the data for a data warehouse. Additional data cleaning can be performed to detect and remove redundancies that may have resulted from data integration. Data reduction. Data reduction obtains a reduced representation of the data set that is much smaller in volume, yet produces the same or almost the same analytical results. Data reduction strategies include dimensionality reduction and numerosity reduction. In dimensionality reduction, data encoding schemes are applied so as to obtain a reduced or compressed representation of the original data. Examples include data compression techniques such as wavelet transforms and principal components analysis, attribute subset selection, for example, removing irrelevant attributes, and attribute construction, for example, where a small set of more useful attributes is derived from the original set. In numerosity reduction, the data are replaced by alternate, smaller representations using parametric models, that is, regression or log linear models, or non-parametric models such as histograms, clusters, sampling, or data aggregation. Data transformation. In data transformation, the data are transformed or consolidated into forms appropriate for mining. Strategies for data transformation include the following. Smoothing works to remove noise from the data. Techniques include binning, regression, and clustering. Attribute construction or feature construction, where new attributes are constructed and added from the given set of attributes to help the mining process. Aggregation, where summary or aggregation operations are applied to the data. For example, the daily sales data may be aggregated so as to compute monthly and annual total amounts. This step is typically used in constructing a data cube for data analysis at multiple abstraction levels. Normalization, where the attribute data are scaled so as to fall within a smaller range, such as -1 to 1 or 0 to 1.0. Discretization, where the raw values of a numeric attribute, such as age, are replaced by interval tables, for example, 0 to 10, 11 to 20, etc., or conceptual labels, such as youth, adult, senior. The labels in turn can be recursively organized into higher-level concepts, resulting in a concept hierarchy for the numeric attribute. Concept hierarchy generation for nominal data, where attributes such as street can be generalized to higher-level concepts like city or country. Many hierarchies for nominal attributes are implicit within the database schema and can be automatically defined at the schema definition level. Data transformation by normalization. The measurement unit used can affect the data analysis. Normalizing the data attempts to give all attributes an equal. Normalization is particularly useful for classification algorithms involving neural networks or distance measurements such as nearest neighbor classification and clustering. In using the neural network backpropagation algorithm for classification mining, normalizing the input values for each attribute measured in the training tuples will help speed up the learning phase. For distance-based methods, normalization helps prevent attributes with initially large ranges, such as income, from outweighing attributes with initially smaller ranges, such as binary attributes. It is also useful when given no prior knowledge of the data. There are many methods for data normalization. We study min-max normalization, z-score normalization, and normalization by decimal scaling. Definition and specification of a generic data mining task. Data mining tasks can be classified into two categories: descriptive and predictive. Descriptive mining tasks characterize the general properties of the data in the database. Predictive mining tasks perform inference on the current data in order to make predictions. Concept, class description, characterization, and discrimination. Data can be associated with classes or concepts. It can be useful to describe individual classes and concepts in summarized, concise, and yet precise terms. Such descriptions of a class or concept are called class concept descriptions. These descriptions can be derived via data characterization, that is, by summarizing the data of the class under study, often called the target class in general terms, or data discrimination, by comparison of the target class with one or a set of comparative classes, often called the contrasting classes, or both data characterization and discrimination. Data characterization is a summarization of the general characteristics or features of a target class of data. The data corresponding to the user-specified class are typically collected by a query. There are several methods for effective data summarization and characterization. For instance, the data cube-based OLAP rollup operation can be used to perform user-controlled data summarization along a specified dimension. An attribute-oriented induction technique can be used to perform data generalization and characterization without step-by-step user interaction. The output of data characterization can be presented in various forms. Examples include pie charts, bar charts, curves, multidimensional data cubes, and multidimensional tables, including crosstabs. The resulting descriptions can also be presented as generalized relations or in rule form, called characteristic rules. Data discrimination is a comparison of the general features of the target class data objects against the general features of objects from one or multiple contrasting classes. The target and contrasting classes can be specified by a user, and the corresponding data objects can be retrieved through database queries. The methods used for data discrimination are similar to those used for data characterization. How are discrimination descriptions output? The forms of output presentation are similar to those for characteristic descriptions, although discrimination descriptions should include comparative measures that help to distinguish between target and contrasting classes. Discrimination descriptions expressed in the form of rules are referred to as discriminant rules. Mining frequent patterns, associations, and correlations. Frequent patterns, as the name suggests, are patterns that occur frequently in data. There are many kinds of frequent patterns, including frequent item sets, frequent subsequences, also known as sequential patterns, and frequent substructures. A frequent item set typically refers to a set of items that often appear together in a transactional data set. For example, milk and bread, which are frequently bought together in grocery stores by many customers. A frequently occurring subsequence, such as the pattern that customers tend to purchase first a laptop, followed by a digital camera, and then a memory card, is a frequent sequential pattern. A substructure can refer to different structural forms, such as graphs, trees, or lattices, that may be combined with item sets or subsequences. If a substructure occurs frequently, it is called a frequent structured pattern. Mining frequent pattern leads to the discovery of interesting associations and correlations within data. Classification and regression for predictive analysis. Classification is the process of finding a model or function that describes and distinguishes data classes or concepts. The models are derived based on the analysis of a set of training data, that is, data objects for which the class labels are known. The model is used to predict the class label of objects for which the class label is unknown. A decision tree is a flow chart-like tree structure where each node denotes a test on an attribute value. Each branch represents an outcome of the test, and tree leaves represent classes or class distributions. Decision trees can easily be converted to classification rules. A neural network, when used for classification, is typically a collection of neuron-like processing units with weighted connections between the units. Regression is used to predict missing or unavailable numerical data values rather than discrete class labels. The term prediction refers to both numeric prediction and class label prediction. Regression analysis is a statistical methodology that is most often used for numeric prediction, although other methods exist as well. Regression also encompasses the identification of distribution trends based on the available data. Classification and regression may need to be preceded by relevance analysis, which attempts to identify attributes that are significantly relevant to the classification and regression process. Cluster analysis. Unlike classification and regression, which analyze class-labeled training data sets, clustering analyzes data objects without consulting class labels. In many cases, class-labeled data may simply not exist at the beginning. Clustering can be used to generate class labels for a group of data. The objects are clustered or grouped based on the principle of maximizing the intra-class similarity and minimizing the inter-class similarity. That is, clusters of objects are formed so that objects within a cluster have high similarity in comparison to one another, but are rather dissimilar to objects in other clusters. Each cluster so formed can be viewed as a class of objects from which rules can be derived. Clustering can also facilitate taxonomy formation, that is, the organization of observations into a hierarchy of classes that group similar events together. Outlier analysis. A data set may contain objects that do not comply with the general behavior or model of the data. These data objects are outliers. Many data mining methods discard outliers as noise or exceptions. However, in some applications, such as fraud detection, the rare events can be more interesting than the more regularly occurring ones. The analysis of outlier data is referred to as outlier analysis or anomaly mining. Outliers may be detected using statistical tests that assume a distribution or probability model for the data, or using distance measures where objects that are remote from any other cluster are considered outliers. Rather than using statistical or distance measures, density-based methods may identify outliers in a local region, although they look normal from a global statistical distribution view. Description of data mining query language with few example queries. Data mining query language. The importance of the design of a good data mining query language can also be seen from observing the history of relational database systems. Relational database systems have dominated the database market for decades. The standardization of relational query languages, which occurred at the early stages of relational database development, is widely credited for the success of the relational database field. Although each commercial relational database system has its own graphical user interface, the underlying core of each interface is a standard relational query language. The standardization of relational query languages provided a foundation on which relational systems were developed and evolved. It facilitated information exchange and technology transfer and promoted commercialization and wide acceptance of relational database technology. The recent standardization activities in database systems, such as work relating to SQL3 and so on, further illustrate the importance of having a standard database language for success in the development and commercialization of database systems. Hence, having a good query language for data mining may help standardize the development of platforms for data mining systems. Designing a comprehensive data mining language is challenging because data mining covers a wide spectrum of tasks from data characterization to mining association rules, data classification, and evolution analysis. Each task has different requirements. The design of an effective data mining query language requires a deep understanding of the power, limitation, and underlying mechanisms of the various kinds of data mining tasks. Primitives for defining a data mining task in the form of data mining query. The set of task-relevant data to be mined, the kind of knowledge to be mined, the background to be mined, the background knowledge to be used in the discovery process, the interestingness measures and thresholds for pattern evaluation, the expected representation for visualizing the discovered patterns. Based on these primitives, we design a query language for data mining called DMQL, Data Mining Query Language. DMQL allows ad hoc mining of several kinds of knowledge from relational databases and data warehouses at multiple levels of abstraction. The language adopts an SQL-like syntax so that it can easily be integrated with the relational query language SQL. The syntax of DMQL is defined in an extended BNF grammar where square brackets represent 0 or 1 occurrence, curly brace represents 0 or more occurrences, and words in sans serif font represent keywords. Syntax for task-relevant data specifications. The first step in defining a data mining task is the specification of the task-relevant data, that is, the data on which mining is to be performed. This involves specifying the database and tables or data warehouse containing the relevant data, conditions for selecting the relevant data, the relevant attributes or dimensions for exploration, and instructions regarding the order or grouping of the data retried. DMQL provides clauses for the specification of such information as follows. Use database name, or use the data warehouse name. The use clause directs the mining task to the database or data warehouse specified. From relational, cube, where condition. The from and where classes respectively specify the database tables or data cubes involved and the conditions defining the data to be retrieved. DMQL equal to DMQL statement. DMQL statement equals data mining statement or concept hierarchy dimension statement or visualization and presentation. A series of data mining statements are shown in the subsequent slides. In relevance to attribute or dimension list. This clause lists the attribute or dimensions for exploration. Order by order list. The order by clause specifies the sorting order of the task relevant data. Group by, grouping list. The group by clause specifies criteria for grouping the data. Having condition. The having clause specifies the condition by which groups of data are considered relevant. Example. This example shows how to use DMQL to specify task-relevant data, the mining of associations between items frequently purchased at AB company by Sri Lankan customers with respect to customer income and age. In addition, the user specifies that the data are to be grouped by date. The data are retrieved from a relational database. The example can be seen on screen. Characterization. Mine knowledge specification == mine characteristics as pattern name. Analyze measures. This specifies that characteristic descriptions are to be mined. The analyze clause, when used for characterization, specifies aggregate measure such as count, sum, or count percentage, the percentage of tuples in the relevant data set with the specified characteristics. These measures are to be computed for each data characteristic found. Syntax for concept hierarchy specification. Concept hierarchies allow the mining of knowledge at multiple levels of abstraction. In order to accommodate the different viewpoints of users with regard to the data, there may be more than one concept hierarchy per attribute or dimension. For instance, some users may prefer to organize branch locations by provinces and states, while others may prefer to organize them according to languages used. In such cases, a user can indicate which concept hierarchy is to be used with statement use. Hierarchy name for attribute dimension. Otherwise, a default hierarchy per attribute or dimension is used. Syntax for interestingness measure specification. The user can help control the number of uninteresting patterns returned by the data mining system by specifying measures of pattern interestingness and their corresponding thresholds. Interestingness measures and thresholds can be specified by the user with the statement with interest measure name or threshold value. Syntax for pattern presentation and visualization specification. How can users specify the forms of presentation and visualization to be used in displaying the discovered patterns? Our data mining query language needs syntax that allows users to specify the display of discovered patterns in one or more forms, including rules, tables, crosstabs, pie or bar charts, decision trees, cubes, curves, or surfaces. We define the DMQL display statement for this purpose, as shown in the subsequent slides. An example of a DMQL query. Suppose as a marketing manager of AB company, you would like to characterize the buying habits of the customers who purchased items priced at no less than ₹100 with respect to the customer's age, the type of item purchased, and the place in which the item was made. For each characteristic discovered, you would like to know the percentage of customers having that characteristic. In particular, you are only interested in purchases made in Sri Lanka and paid for with Visa credit card. You would like to view the resulting descriptions in the form of a table. The data mining query is expressed in DMQL as shown on the screen. Conclusion. In this chapter, we have covered the following in detail. Data pre-processing, including data cleaning, data integration, data transformation, discretization and concept hierarchy generation, definition and specification of a generic data mining task, description of data mining query language with few example queries.